Okay, so I hope you have with you the handout I had told you to print for last class that we never got to. And then we'll go over the participation from Friday. Now, remember, if you're absent and there is participation, which you should know about because you should watch the video when you're absent and see what was assigned. And then you want to send me an email of a picture. Okay, so otherwise you get a 0. So, you know, I'm going to go over this today. Now, according to my syllabus, you have a week to make up participation, but you're only allowed to do that like a maximum of twice. So if people are out sick or out quarantined or something, I expect you to keep up with, keep right up with the participation instead of waiting a week. So anyways, is there anyone who is out on Friday that has this to show me? Okay. So anyways, we'll go over this, and then I was hoping, I know that not everyone, the homework's going to be due Monday, September 18th, the day of the quiz. Okay. And the content for the quiz, there will be some review questions. So there will be an equation of a line, factor this quadratic, a couple of things that have been on the review assignments. And then the rest of the content will be limits up through what we get to on Wednesday. So we're going to look at limits from all different representations. Okay. So in this case, we would say, so wait, I don't want to write on this paper because I'm going to have class later, like for y sub 3, right? For this equation, we would say that the limit as x approaches 3. Okay, so the limit is always what number we're getting really, really close to, the x. And we'll call this f of x. Okay, we write the function here, and then we say what it is that we get really, really close to. So notice in this case, I'm never going to get 6 as an output. Okay. So does the limit for y sub 3, does the limit exist though? In y sub 3. Looking at that table of values, does the limit exist? The limit exists. What is it that doesn't exist? What is it? The y value, the functional values, right? So I would say for y sub 3, I would say f of 3 dne does not exist, but the lit is 6. So we're going to explore this a little bit more today, but I was hoping as you looked at the homework you did over the weekend and you noticed that when I have a limit and not a functional value, we're going to start looking at, well, what's happened? What does that look like on the graph? Okay, does that look like an asymptote line? Is that a hole? Right? What are your instincts saying? Because there's nothing there at 6. Do you think there's a hole in the graph or a vertical asymptote line? What do you think? A hole. Yes, there is a hole in the graph because we're getting really, really close to some value, right? So it's going to look like this on the graph. And here's where, if this is our x-axis and this is our y-axis, there's the 0.36. There's a hole there. Okay. Now, so the main one that people had trouble with on here was, okay, let's see, where does the limit exist? So the limit exists for functions y2 and y3. It does not exist for y sub 1. Okay, because remember, limit means we can get really, really close to something. Okay, sub y value. Okay, what do you think is happening there then in y sub 1? Like numbers are getting bigger and bigger. And if I got a little closer to 3, I'd see a number like 100,000. And if I got even closer to 3, I'd see a number like 1,000,000, right? And when I see really big numbers, one's positive and one's negative, that tells me I have a what kind of feature in the graph? Asymptote line. Okay, so Ryan says asymptote line, he's correct. Okay. So notice the limit does not exist here because I'm not getting close to some value. So we need to be able to recognize what's happening on a table of values. So let me really quickly, now if you weren't here Friday, well, actually, I'm going to post the answers to these online, but I think people had the most trouble with number 1, okay? The function that's defined, I think that's pretty easy. This one's defined. These are not defined, right? And notice the limit equals the functional value, okay? So we saw that a little bit in the last class, that the limit and the functional value can actually be the same thing, right? Or one can exist and not the other and vice versa. We're going to look at a chart today of like all the different possible scenarios, okay? And this is your clue when you look at a table of values. This should be your clue that you're looking at an asymptote line. So let's go over to class examples for limits. And let's see, let me zoom out enough. Okay, so we're going to find a whole bunch of limits, and actually I'm going to save the second half of this for you to do for participation. Okay, so first of all, -10. Okay, so remember, these are x values. And what we're going to do over on the side is we're going to make a list of points of discontinuity. Okay, we haven't officially defined yet what it means for a function to be continuous, but I think you have a pretty good sense, and you probably talked a little bit about continuous functions in high school. All right, so you have this sense that if it's continuous, you could draw it without picking up your pencil, right? There's no holes in it. There's no asymptote lines. Now, when it comes to giving a definition, if I say a continuous function is a function with no holes or asymptote lines, that's a poor definition because definitions need to be stated in the positive, not in the negative. So you need to say what features it does have, not what features it doesn't have. That's why when I gave you a definition of polynomial, and I said, well, it has many terms, although it could only have one term. Poly means many, right? So it could have many terms, and none of the exponents can be fractions or negatives, right? That's really a poor definition because I said what it can't have, not what it does have. Okay, so we need to at some point get a good definition of continuity that's a proper definition. Okay, but I think you're going to have an intuitive sense of when we're not, when something's discontinuous. So here, if I looked at -10, I'm going to zoom right in here. Okay, now I didn't ask you this, but let's write it up above. What's f of -10? Right? What's the functional value at -10? That would be 1, positive 1. And if I took my little guy and I stood my person really close to -10, so I stand at -10.000001, or I stand at -9.9999999, so I'm really close to -10, what would I see functional values close to? What would that be? What would the limit be? So my guy's standing right here, and they see functional values close to, well, what y value is right here? That's 1, right? So notice here, the limit and the functional value are the same. Okay, so we look at the graph and we say, well, nothing interesting is happening at 10. Right, so I've got this handout where all this crazy stuff is happening. There's asymptote lines, there's holes, there's what we call jumps, right? But nothing interesting happened at -10. Okay, so now I'm going to look at -8. Okay, and I have a hole here in the graph at -8. Okay, so what that tells me is the functional value does not exist. Okay, and it tells me this is a point of discontinuity. So leave a little room next to this because we're going to write more about like why it's discontinuous. I mean, discontinuous because there's a hole there, but we're gonna write that in more like based on the definition, okay? But so remember, I'm going to approach -8. I'm not actually going to step on -8. Okay, so I just get close to -8. What functional values am I close to? All right, so this is 2, so this is 3. Okay, because the arrow means get close to it. It doesn't mean step on it, right? So if I just stand close to it, and I do have to stand close from either side, right? And see the same values. If I don't see the same values on either side, then the limit doesn't exist, okay? So I've got a case here where the functional value doesn't exist, but the limit does. I have a case where both exist and they're the same. So let's look at -6. Now it starts off from the left. So if I walked up to -6 from the left, so here's my little person standing right there. And there's an asymptote line here. What kind of numbers am I seeing when I look up? Right, so asymptote lines they take off, right? So I see functional values that are really big, right? Right, going to infinity. So again, I have a discontinuity here at -6. Okay, and on the other side, I see functional values approaching -infinity. So this is where on your table of values, you'd see values like 10,000, 100,000, right? Big numbers, right? And usually one's positive and one's negative, although it is possible to have a vertical asymptote line and it goes to infinity, like watch. You don't have to draw this or anything, but I could have a vertical asymptote line that goes like this, where the function goes like that, right? And on the left and the right, we go to positive infinity. But often it's one direction, one way, the other direction, the other way, okay? Often, but not always, okay? So this is a does not exist. So we have a case here where the functional value doesn't exist, right? The limit doesn't exist. Okay, so -3 is kind of interesting. So at -3, the functional value is the dot, right? Sometimes people don't even like notice, like, oh, wait, there's a hole, but then I have a dot filled in somewhere else. So if I just stood on -3, I would see the functional value down here, which is also -3. Okay, because that's where the closed circle is. Oh, wait, I'm sorry. That needs to be on f of. F of -3 is -3. Okay, but if I just stood close to -3 on either side, so you got a guy standing on the left, you got a guy standing on the right, saying, okay, I see functional values and they are close to, and then what would it be? 1, okay? So again, we notice at a hole, the limit exists. Okay, so this should equal 1. Okay, so last one that we do together, and then we'll do, I'm going to save half of this for you to work on your own. So -1. So notice I have this thing where, remember this means from the left, from the right. Okay, and the two sides have to match in order for the limit to exist. Okay, so if I go to -1 and I stand somebody on the left of -1, somebody on the right of -1, and they're both looking up, they're seeing different values. Okay, so you try to decide, what's the guy on the left seeing values get close to? What's the guy on the right seeing values getting close to? Okay, remember, limits are always y values. Okay, so the guy on the left sees values close to 4. And actually, there's a closed circle there at 4, right? That's where the circle is closed. So what that means is if I actually step on -1, I get an output of 4. That's the functional value. Okay, because that's where the closed circle is. Now to the right, can I say the limit exists even though the circle's open? Right, I can, because what limit means is if I get close to -1, so it means I don't have to actually get a value of 6. I just have to, if I'm right here, I see a value like 5.9999, right? So even though the circle is open at 6, I still get close to 6. I just don't actually get to it, but that's okay for the limit. Okay, so this is a case where the left hand and the right hand side, they don't match. Okay, and so if the left and the right hand side don't match, then the limit, we say, doesn't exist. Okay, so the limit only exists if you see the same value from both sides. And we haven't been adding our points of discontinuity. So we also had a point of discontinuity because there was that hole, a hole here, even though the point was defined somewhere else. X equals -3 is a point of discontinuity. So is X equals -1. And so we're going to label these at some point in the near future with what types we call them, what type of point discontinuity, and what part of the definition. We're going to get a good definition of continuity that's stated in the positive, not the negative. Okay, so I'm going to leave the rest for you guys to work on. So if you want to put that away, so here's something that we've noticed. Okay, so let's write down all, I'm zoomed way in, I don't need to be zoomed that in. All possible cases with limit and functional value. And I'm going to abbreviate that FB so I don't have to write functional value out over and over again. Okay, so one thing that's possible is that the limit does not exist, DNE, but the functional value does. So we can have every possible scenario where one exists, the other doesn't, and then vice versa. We can have a scenario where neither exists. We can have a scenario where both exist. Okay, so every possible scenario here. So the next one would be that the limit exists, but the functional value, DNE. So you want to be able to think about, we're going to start talking about, well, what would this look like on a graph? Or what would this look like on a table of values? Okay, so the limit exists, but the functional value doesn't, or the limit doesn't exist, but the functional value does. We can have neither exist. All right, so limit DNE, functional value does not exist. So we could have a point where neither one exists. Or we could have both. Limit exists and the functional value exists. Right, and then when this happens, we can have different things happening. Okay, because when we were just doing this paper, -10 was not very exciting, right? There was no excitement at -10. Nothing out of the ordinary, just a continuous function through the point, right? And we noticed that the limit and the functional value were the same. And we did that a little bit in the last class too, where we looked at that one problem from the lab that had a hole, but then we looked at limits at other places and the limits were always the functional values, right? Everywhere other than at that hole, the limit was just the functional value. So they can be the same, right? So the values can be the same, or they can both exist, but the values are different. Okay, so think about what it looked like on the graph when we just saw that. Okay, because we actually saw that at -3 on the graph, where both existed, right? If I stepped on -3, my output was -3, but the limit was 1. Okay, so they both existed, but they were different. So these are all of our possible scenarios. So let's make a list of, because I like to compare and contrast, and also, let's really focus on then what the limit tells us about what's happening graphically. Okay, so find the limit. We're going to put that on one side, and then we're going to say, what is happening graphically? At that value of x, right? Because we're not going to learn about the entire graph of the function. We're going to find the limit at some values of x, and then we're going to say, okay, well then at that value of x, what does the graph look like? Okay, and so I hope you recall, so this is from the other day, that we looked at this function. Oh wait, let me write it like this. This was the weird one on the left. So the limit is x approach 2, and we had this. And we looked at it on the table of values, and we saw 3.99999 and 4.00001, right? So that's what happened on Friday when we looked at the table of values. So we said this limit is 4. So what's happening graphically? F of 2. F of 2 did not exist because we got an error on the calculator, but then there was a hole at the point 2, 4. Okay, so we're supposed to be trying to think about what creates a hole in the graph versus an asymptote line in the graph. And so that's why I was hoping you did the homework over the weekend, because there was a place where, you were looking at the table of values, but then there was a place where you were told to factor and look at the factors and see, see what was happening based on looking at it in factored form. So here's something else that we looked at on Friday. We looked at this function from our lab, right? And this function, the limit does not exist. And we had a vertical asymptote line at x equals 1. Okay, so we're supposed to be thinking about why would I have a hole in number 1 and not, but an asymptote line in number 2? Okay, and also remember that, like with this function up here, we did look at other limits. I forgot exactly what other things we plugged in, but we looked at like the limit as x approached 1, I think, for this function. And there's no coincidence that if I divide these factors, divide this to 1, right, I would just plug in and get 3, right? So what that means is that there's just a point at 1, 3, right? Or we could say f is continuous at x equals 1. Okay, because if we looked at the graph there, because actually when you looked at this, it looked like a straight line. The reason it looked like a straight line is it was missing 1 pixel, and you couldn't see the 1 pixel in your calculator that was missing. So it just looked like a straight line. Right? So last night's homework, you were asked about this function. So let's see, it factored to f of x equals, let's see, x minus 5, x plus 1. And then in the bottom, it was, so this was one of the homework problems. Okay, so you were asked to find limit as x approached -1 and as x approached 4. Okay, so that's what you were asked to find. Okay, and so if you looked on the table of values, because last night's homework was all about just graph the function, look at the table of values, make your change by x, 0.001, see what's happening close. I hope you noticed that the limit did exist when x was -1. It ended up being -6 over -5, which is 1.2. And this limit did not exist. Okay, so then that tells me something about what's happening graphically. So if you took this function and you looked at the graph, what's happening graphically here is that at x equals 4, there's a vertical asymptote line. But then there's a hole in the graph at -1, 1.2. Okay, so as we analyze, like, when did I get a hole? I got a hole here at -1. Got a hole here at 2. Do we see a common theme for when we end up with a hole in the graph? If it'll factor out, right? Because what happens is if we can cancel, or, well, I shouldn't say cancel, divide to 1. If we can take this and divide to 1, then we can just plug in, right? The problem is, though, I'm not allowed to divide this to 1 if x equals -1, but that's where limit is clever, and they say x isn't really -1, it's just close. Because it's just close to -1, we can divide this to 1, but then at the end, we're kind of like, just kidding. We said it wasn't -1, but now we're going to plug in -1. Okay. So let's look at something like, let's look at these two. So let's look at limit as x approaches 4 for this function. And see if you can decide what's happening graphically. And let's look at limit as x approaches 3 for this function. Okay, so I'm not allowed to cancel. I'm not allowed to divide x minus 4 by x minus 4 if x is 4. That's not. Right, it's not. So I can say, well, these divide to 1, therefore the limit is 8, right? I just plug into what's left. Is there any way you're gonna do anything algebraically in number 6 with that? I mean, nothing's gonna cancel. What do you think there is at x equals 3 there? Well, first of all, what's happening here when x is 4? What do I have at x equals 4? And number 5. A hole, right? So I have a hole at 4, 8. Okay. Notice hole limit exists, right? Hole limit exists. Hole limit exists. Okay, and we see that over here in the pictures, right? Every time there was just a hole in the graph, right, the limit existed. It was whatever, you know, basically whatever y value had the hole at it, right? Because we can get very, very close to that value of y. So what do you think is happening graphically here at 3? It doesn't behave like any of these. Asymptote. Those are our only two choices for discontinuities, right? There's either a hole or an asymptote line, right? For when the denominator is 0. So here we have a vertical asymptote line. I'll write it out. Vertical asymptote line at x equals 3. Now, if nothing interesting is happening. Okay, so I'm going to look at these same functions again, but this time I'm going to find the limit as x approaches, I don't know, 7. Right, for this same function. And then for the same function that was in number 6, let's look at the limit as x approaches 2. Okay, so remember, if I can simplify it, I can use the simplified version. Okay, so I can divide that to 1, those x minus 4s, and say, well, this is just the same as that. Okay, is there a hole at 7? There's a hole at 7? Or is the function, there's a just continuous at 7? You think, because I get this limit to be 11. But if I asked what f of 7 was, right? F of 7 is 11, right? So the point 7, 11 is on the graph. Right, so f is continuous at x equals 7. So anywhere else other than 4 for that function, the limit and the functional value are the same. Okay, so wherever a function's continuous, right, the only places where we have to sort of worry about weird stuff with the limits are places where the function is discontinuous. So in that case, if I gave you, oh, wait, let's look at this one. Is this undefined because I get 0 on the top? No, right? I can have 0 on the top. This is 0. Okay, so what this means is that f of 2 is 0, or in other words, the point 2, 0 lies on the graph. What's special about the point where y is 0? What kind of point is that? X-intercept, wonderful, okay? So this would mean that this is an x-intercept, or we call that a root, or we call that a solution. Okay, so notice that when the numerator is 0, that gives us our x-intercepts. Okay, so let's look at if I had a polynomial. All right, so as we said, if nothing interesting is happening in our function, okay, so I give you something like this, x cubed minus 2x plus 1, and I ask you for that limit. It's a polynomial. Are there any holes in it? Or asymptote lines? Right, so that's one of the things we love about polynomials is there no holes, no asymptote lines, the domain's all reals, right? Which means then, if I want to find the limit, right, I just plug in. Okay, so the limit, so I'm going to say this over here, the limit will always equal functional value for a polynomial. Right, because there's no holes, there's no vertical asymptote lines, nothing interesting is happening, right? So here we've got the point 2, let's see, 8 minus 4 is 4 plus 1 is 5. Is that right? So the 0.25 lies on the function, lies on F. Okay, so let's do one more kind of big, long, complicated problem. So we're going to look at one problem with a whole bunch of questions. And I don't know about you, but I've got to go on to another page. Okay, so here's my f of x. And we are going to find limits as, and I'm going to give you a whole bunch, and then you're going to try to say what's happening graphically then at that point. So as x approaches -5, x approaches -2, 0, x approaches 1, x approaches 6, right? So I recommend factoring. I don't recommend just starting to plug numbers in. So these divide to 1 as long as x does not equal -5. I can divide those to 1. Right? So it is totally fine to then work with this in a simplified form, keeping in mind that I was only allowed to divide them to 1 if x is not -5. But luckily, I never say x is -5, right? I just say it's close to it. And that's what limit is. I'm close to -5. Okay, so I will expect you to do simple integer work like this on a quiz without a calculator. I should have given myself some more space. There's nothing I can do at -2. I get a 0 on the bottom. That's not allowed. Okay, and now at this point, I'm just plugging in. Right, plug into the simplified version. So this would be -1/2. This would be 0. This would be 5/6, 5/8. Okay, so you should be listing over on the right then. We have a whole, we have an asymptote line, and then we have places where the function's just continuous. Okay, so try to get what's what. There's a whole, there's an asymptote line, and then there's just points that exist on this function. Right, and let's actually write the domain of this function before we check our answers. Okay, so domain of the function, you look back up at the original and you say, well, what are the only values x cannot be? X cannot be a value that puts 0 in the denominator. Those are my only restrictions. Okay, so these are the only values missing from the domain. Okay, so you do the thing with the parentheses. I'll get you started. Right, -infinity, comma. Right, so do the thing with the parentheses. So it's so helpful to use the number line to get this. So one of the things when we're talking about continuity, this function is continuous everywhere other than -2 and -5, right? So like, as far as continuity, if I looked at, if I went up here and said, well, where's the function continuous? What values of x, right, that I looked at? Okay, and it would be everything except these two values, right? So here, f is continuous. Okay, so if I have a rational function, I'm going to say this, a rational function is continuous over its domain. I could say that about many functions. I mean, a polynomial is continuous for its domain. Its domain is all real numbers, right? And it's continuous for all real numbers. So I could have put polynomial in there. I could have put algebraic. I'm going to show you in a few minutes, though, a function that's not continuous over its domain. So anyways, f is continuous here. Okay, so what do we have going on? Where's the hole in this graph? At what point? Emily, you look like you know. Perfect, right? So we have a whole at -5, 2. So remember, key for whole, limit exists, right? Where do we have an asymptote line? -2, so x equals -2. There's a vertical asymptote line. And for the rest of these, right, these points lie on the graph, okay? And the graph is continuous at all of these points. So we have these points 0, -1/2. We have the point 1, 0, right? We have the point 6, 5, 8, right? These are just points on the graph, and F is continuous at all those points. What's special about this point when X is 0? What kind of point is this? Y-intercept. So this is the Y-intercept right here. And then this would be the X-intercept. So notice the X-intercept occurs, right, when I'm working with a rational function. This occurs when the numerator, right, the numerator is 0. That's how we make a fraction equal 0, is make the numerator equals 0. Okay, good. So let's see. Boy, this long block feels extra long today. So let's look at another type of function called piecewise. And I think you did a little bit of this in high school, maybe, probably. And I hate that they do this in high school because I think you cannot really understand a piecewise graph without understanding limits. Okay. So I hate it when they do it in high school because you don't know limits yet. So let's say I were doing, now when I give you these, I promise to always give you really simple functions. All right, so I'm going to make it really easy. Okay, so let's do X is, oops, I'm sorry. X is less than 3. And then we'll just do like X plus 1 for X. Oh, sorry, I'm writing. X is greater than or equal to 3. Okay, so just like they sound, the function is defined in pieces. Right? And so I'm going to give you graphs that you know what they look like, right? There's a standard parabola, right? You should be able to draw them, no problem, right? X plus 1, that's just a straight line with a slope of 1 and a y-intercept of also 1. Okay, so I'm going to give you easy functions here. And then what we're going to look at, though, is we're going to look at some different limits. So limit as, so we're going to take a look at X approaches 3 from the left, X approaches 3 from the right, X approaches 3. We'll look for F of 3. I don't know, we'll do F of 1 and the limit, wait, let's see, X approaches 1. Okay, so my best advice for drawing piecewise functions is that you put the 3. So this is where it changes. So do what your high school teacher taught you to do, where you were taught to make a table of values. Put 3 on there twice, and then get a few values less than, and then a few values greater than. Although you should know that that's going to be a parabola. It's just going to end on the right hand side when X is 3. And then you're going to switch to a straight line when X is 3. Right? But if you approach this the way your high school teacher taught you, now, first of all, X, I cannot have an input with 2 different outputs. Okay, so that would be like me going up to the vending machine, typing in A3, and not knowing if I'm going to get Skittles or M&Ms, right? So I can't have one input go to two different outputs. But that's not actually going to happen because here X is less than 3, but X can get all the way up to 2.9999999999999, right? It just has to stay less than 3. So what's going to happen on this side of things, and I always put a line here to like distinguish when I'm going to switch from one piece to the next. This is going to be an open circle, right? Because when I say, you know, that if I plugged in 3, I'd get 9. I'm not really plugging in 3. I'm plugging in 2.99999999999, right? Which means I'm going to get 8.999999999, right? But I'm going to say, well, I'm going to call this limit. The limit is 9. And so that'll be an open circle there. Okay. And then, so again, this is a nice, easy problem, but here, because of the equal sign, right? F of 3, right? So if I say, what's the functional value at 3, I look at where there's the equal sign, right? And the functional value is actually 4. Okay, because that's where the equal sign is. So that's where the closed circle is. Okay, so then, so let's see. So 4 would be 5, 5 would be 6, right? So this should be an easy graph to draw. And I'm just looking for a rough sketch. Okay, so 3, 9 is an open circle. And then I know my parabola goes like this, right? So you have to have some knowledge. It should be hitting there, 0, 0. Okay, so I have that open circle, which means then what's the limit as X approaches 3 from the left? That would be what? The limit would be, what am I getting close to? What am I getting close to? 9. Okay, so that's the limit. But on the other side, so let's say I have my closed circle here, and then the function takes off like that. Right? The domain here is all real numbers. So that's why I have to be careful saying that a function's continuous for its domain. Right? Many functions are like rational functions, polynomials, but here the domain is all reals. Okay, so then this would be 4. And then what happens when my limits don't match? What do I say about the limit? Doesn't exist. I didn't leave myself enough room. So DNE. And then like, what if I asked you about f of 1 and then the limit as x approaches 1? Right, so f of 1. Right, and the limit as x approaches 1. Nothing exciting is happening at 1. What's f of 1? Less than 3, so I'm using this piece, right? So 1 squared is 1, and then what would the limit be? 1, right? So again, limit and functional value are the same. So we're going to have to start using this information to get a good definition of continuous. Like, how do we say a function is continuous without saying what it doesn't have? How are we going to say continuous in terms of what it does have? Okay, so right now we're going to do participation. So you need to finish this and then do this. Okay, and I will take a piece of paper from every group. Okay, so if you are watching this remotely, you need to complete these exercises. Gosh, this is a little hard to see, isn't it? Because I have something on the back of it. I try to save trees by writing on the back of old scrap paper. Is happening graphically at.
Yeah. I know it's. You know, speaking.
All right, so write these answers. Have somebody write these answers on a separate piece of paper. And then obviously the other answers can get written right on your paper. There's my answer. All right, so I'm going to end the recording because we're going to just work for the last 15 minutes.